Hey engineers, Timmy here, and in this video I'll be showing you how to solve Leetcode 2040, find the kth smallest product of two sorted arrays. Let's get into the video. Okay, so let's get straight to the problem. So we're given two sorted zero-based indexed integer arrays called nums1 and nums2, as well as an integer k. We should return the kth smallest product of nums1 of I times nums2 of j, where I is greater than 0 but less than the length of nums1, and j is also greater than 0 but less than the length of nums2. And we're giving an example here where nums1 has 2, 5, nums2 has 3, 4, and k is 2. And when you multiply the product of both of them, you get 2 times 3, 6, 2 times 4, 8, 5 times 3, 15, 5 times 4, 20, and the second and k, which is the second smallest element, will be basically 8 because 2 times 4 will give us 8 when you sort it. That's pretty much very simple. But why is this a hard problem? Well, this is a hard problem because of the constraints. And it says here that for the length of nums1 and num2, we have at least one element. So the length of nums1 and nums2 is at least greater than 1, and at most not greater than 5 times 10 raised to power. So basically 50. So the length of nums1 and nums2 is between 1 and 50,000, right? Inclusive of 50,000. And here it also says that for every element in nums1 and num2, it is at least 10 raised to power negative 10 raised to power 5, and at most negative 10 raised to power 5, and at most positive 10 raised to power 5 inclusive. So what that's telling us is that, let me just see if I can write it. So what that's telling us is that for every element in both arrays, they can be between negative 10 raised to power 5 and positive 10 raised to power 5. And if you then think about this, it means that each product value can basically, so meaning if one number is say 100,000, and you multiply 100,000 negative 100,000 by say positive 100,000, right? It means that at most you could get your range of product values is between negative 10 raised to power 10 and positive 10 raised to power 10. Guys, I'm not a math expert, right? I had to do a lot of reading for this problem, right? But I hope I'm really explaining it well and you understand what I'm explaining. And the way we just get this is that so 10 raised to power 5 times 10 raised to power 5 gives us let's just do for positive for now, gives us basically 10 raised to power 5 plus 5, which is then 10 raised to power 10. So this is what the product value between of multiplying a number in A and B could possibly be. Right? And that is very important. We'll come back to that. Right. So let's just read the constraints on. Okay, and the length and K is at least 1, but at most the the length of nums1 and nums2 multiplied together, right, inclusive of that. And again, another very important constraint that we're giving it, that nums1 and nums2 are sorted, right? Now, when I was reading this, someone said if you see a question that says find the kth anything, and I'm including this, and your input values are sorted, your what should be ringing in your head is binary search. But before we move to binary search, let me just explain a couple of things. Now, the brute force approach is basically you iterate over nums1 and nums2, obtain all the products of I times j if I is each value in nums1 and j is each value in nums2, multiply them together, and then sort after you've multiplied, and then just return k minus 1 as the k smallest element. But
if you take into account this constraint here, this is not going to it's not going to work. It's basically going to your like the is going to crash, right? And that's not what we want. Now there's another approach where, for example, you can use brute force and binary search, and it works by the idea of that since you know that the largest range of products is between negative 10 raised to power 10 and positive 10 raised to power 10, what you can do is you can then use binary search to define a search space. The approach is basically you take your lowest maximum product value, your highest maximum product value, and then you obtain a mid value between both of them, right? Because you're trying to get what the search space is. You then counting by, say you use a brute force approach, you ready up, let's say you even wrote a code that could possibly obtain all the product values, right? You then obtain a product value, and then you now want to you want to establish what you are looking for is how many this is the equation. If a is each value in norms 1 times b is each value in norms 2, you want to establish how many what's the product of this that is less than equals to mid, right? This is what you want to establish, but now there are caveats. There are caveats that you must handle, and I'll go to what those caveats is in the correct solution, right? And then once you obtain, let's just say you handle those caveats, you obtain count of the products that is less than equals to mid. You can then check if the count of products that is less than equals to mid is greater than equals to k. It means either that value, right, that is currently our mid is either is the kth smallest element or it is greater than the kth smallest element. And what do? You set your high to your mid, and then if it's not, it means that your search space is too low. Then you set your low to be mid plus 1, and at the end of the day, at the end of each iteration, you would basically obtain what your mid value is or what your kth smallest value is, and then you can return it. But that's the explanation on that. Let me go to the correct approach. Now, the correct approach is basically something very similar to the brute force approach and binary search, and it involves using binary search on the possible product value space. That's negative 10 raised to negative, so that is negative 10 raised to, oh no, not this, that is negative 10 raised to power 10 and positive 10 raised to power 10. And then once you've obtained your mid value, you then use binary search again on the on one of the input values. Use binary search on one of the input values, because remember, it says here our inputs are sorted, right? Meaning they are sorted in ascending order. We can basically use binary search to figure out what the mid value is. But now let me just go through my notes here. So I write the same approach as before, but instead of brute forcing the count, we rely on binary search to find values in norms 1 that the product of the numbers in norms 2 will be less than equals to mid. So let's go through an example here. Let A be the values of numbers in norms 1 and B be the values of numbers in norms 2. We want to establish a situation where A times B is less than equals to mid. But the tricky part is that A can be one of three states. A can either be 0, meaning that, for example, if you look at this input, let's look at this example, see here where A is 0. It doesn't matter what you multiply in norms 2, right? It will always give you 0, right? And again, what we want to establish is every possible product that is less than equals to mid. So if A is 0, we will count all of norms 2. We'll count all values in norms 2 if mid is greater than equals to 0. Why? Because if mid is negative, let's say, for example, this calculation we do here, right, results in mid being negative, say negative 1000, for example, right, negative 1000. It doesn't matter this equation, like if A is 0, we won't count all of norms 2, because no, even if norms 2 is, say, all positive integers, what we are trying to establish is the product that is less than equals to mid, and positive integers of norms 2 will never be less than equals to a negative mid. And so this, you would only do this if mid is greater than equals to 0. Now, what about when A is a negative number, meaning is less than 0? then by the law of inequalities, of multiplying the negative number in an inequality, right, it means that a times b less than equals to mid will become b greater than equals to mid divided by a, because what we want to find is the values in b that we can multiply with a that are less than equals to mid. Again, I'll take that again. The values in norms 2 that you will multiply with norms a that are less than equals to mid, right? And for us to then know what those values are, what we can then do is basically it's just balancing the equation, right? You're looking, you're finding b, meaning that mid divided by a will give you b. However, if a is negative, then the inequality sign must flip. That is very important. Now, if a is greater than 0, then it's just direct. Anything that we multiply with b should be less than equals to mid, and so that's we just handle that. And I put here b less than equals to mid divided by a means find all elements in norms 2 that is less than equals to b. That's basically what we're doing. We're trying to find all elements in norms 2 that is less than equals to b. But if b is greater than mid divided by a, we're trying to find all elements in norms 2 that is greater than or equal to b. I hope I haven't lost you there. But please just follow along. I'm sure when we get to the code, it will become clearer. Now, remember that what we this is just us looking for B. We're finding B here. But what we really care about is this. This is what we care about. We want to count how many elements of how many products of A times B are less than equals to mid, which will then tell us the possible values that are the kth smallest element, right? But remember that that is what we really care about, right? And if that is what we care about, it means that b greater than equals to mid. If we are looking for all elements in norms 2 that is greater than equals to b, it means that what we really need to be handling is that all elements or all numbers to the left of the results of this are definitely less than b, right? And the way we just do that is the length of norms 2 minus b greater than equals to mid divided by a is equals to a times b less than equals to mid. Now, again, this is a very, very interesting math problem. So here I say note, because again, another interesting edge case that we have to handle. Note, because a is negative, and dividing a negative sign in an inequality flips the inequality, we have to round up in the direction that keeps the product of a times b. Again, this is what we want. This is really the crux of the matter. This is what we really care about. And I'll give you an example. Let's say mid is 5, a is 2, and we're looking for b in this equation, right? By basically applying, so finding b, that becomes negative 2 times y is less than equals to 5. We divide both sides by negative 2, that will give us y is greater than equals to negative 2.5, because that flips the equation, right? Now, if we round down, meaning that we apply, for example, in Python, we apply the floor function. If we round the floating point number to a whole number, because again, remember, the possible values of norms 1 and norms 2 are whole numbers, right? If we round down, it means that we'll have negative 3. Now, let's see if multiplying negative 3 by a preserves the state of this equation. So I say here, remember, a times y is less than equals to mid. And so if negative 2 times negative 3, if we multiply that, that will give us 6 is less than equals to 5. But that is not mathematically correct, right? That is not mathematically correct. Let me get my marker here. Let me put a big fat wrong here. That is not math. 6 is never less than or equals to 5. But if we decide to round up, right, we round up. Let me get my ink. We round up here by applying, say, the ceil function in Python. It means that rounding up, it means that rounding up, basically negative 2.5 will become negative 2. And when we basically put our number, our values, right, negative 2 times negative 2, missing a less than equals to here, less than equals to 5. Yes. The negative 2 times negative 2, is it less than equals to 5? Absolutely. 4 is less than equals to 5. right? Again, I hope that is very, very clear. And once you get that, will give you the count, and then you can then check if the count of mid is greater than equals to k. Then it means that mid is either greater than equals to the is either greater than equals to k, and so you set your high to mid. Otherwise, it is less than, so you set your low to mid plus one, right? Basic binary search stuff. But let's look at complexity analysis, right? Because it's binary search, in terms of space complexity, it's just big O of one, which is constant space. We don't need any space. But in terms of the time complexity, remember we're using the maximum product, which is 10 raised to power 10, which is the range of negative 10 raised to power 10 to positive 10 raised to power 10, but the maximum product is this. And so, and we're applying a binary search on that. And binary search is a logarithmic search operation. So log 10 base 2 times, remember, we're iterating the values of norms 1 and trying to find all possible pair combinations of the values in norms b, but we're not iterating over b. We're applying binary search to b, which b is the possible values that are in norms 2. So that gives us log of maximum product times log of b. So, and remember, maximum product, this is the possible maximum product we can have, and log 10 billion or 10 raised to power 10 base 2 is approximately 34. And so our time complexity becomes 34 times a times log b base 2, which then gives us big O of a times log b, which is our final time complexity. I hope this explanation was really helpful. Now let's jump into the code of the most optimized approach.
Hi guys, okay, let's get into the video. I've already gone ahead to write the code because I feel the video has gotten too long. But if in other videos you would like me to cover the code and write it down, please let me know and I'll do that. So let's start from here. As we established earlier, the maximum product value range of our numbers is basically negative 10 raised to power 10 and positive 10 raised to power 10, and that's why we set it to low and high. And then we perform binary search, and binary search would involve iterating until low is greater than or equals to high, right? But as long as low is less than high, we obtain our mid value, and then we count how many products of norms 1 and norms 2 is less than equals to mid, and what is the count that is now greater than or equals to k. And what we're trying to establish here is that we're trying to find if mid is equals to our kth value or if it's greater than our kth value, and if any of those two conditions is true, we know that we need to search lower, and so we set our high to be mid. Otherwise, we know that our searching too low, and then we set our low to be mid plus 1. So let's look at the count, which is kind of the tricky part, right? So again, remember, we're trying to find every product of A multiplied by every product of B that is less than equals to mid, right? And so we iterate starting from norms 1. So for every element in norms 1, we check if the current element we're considering is greater than 0, then we do binary search on norms 1 or norms 2 rather. If it's less than 0, we do binary search on norms 2, but then we handle a different edge case. You know what, let me just start from when x is equals to 0. So remember from the explanation, when x is 0, that means it doesn't matter what we multiply in norms 2, because the value will always be 0, and so we can just take the entire length of norms 2 as long as mid is a positive value, meaning it is 0 or greater than 0. Otherwise, we set it to 0. But if x is greater than 0, it means that we need to find every element in norms 2 where mid divided by x, right, is going to give us the count. So that will give us the count of every element where b if b is the current element in norms 2, where b is greater than equals to no, up to mid divided by 2. And bisect, right, works by giving you the index of the position where the current element you're searching for is supposed to be slotted in, meaning that every element to the left of that element is basically less than or equals to that. But here, and because we want to get every element that is less than or equals to b, we have to use bisect right. So that's why we're using bisect right, and that will give us a count. So if you look here, let's say we're searching for 2, right? If you use bisect left, So if you're searching for basically, let's say five, let's say four, right? If you use bisect left, right, this this is the index that will be returned, 0 1. So 1 will be returned, but that's not what you want. You want to get every element that is less than or equals to b, which is what we want. And that, so that will give you that will give you the index here, which is 1, and then you know that the next position is supposed to insert is this. So that's basically just the explanation, right? Otherwise, when x is less than 0, now remember in the example I gave, you need to round up, right? You need to round up when x is a negative number, which is why we're using the ceil function here. So for example, if the division of me divided by 2 is negative 2.5 and we round up, this would be negative 2, and then we use bisect left. So here we're trying to find every element where b is greater than this, where every element in b that is greater than this, calculation. But then that tells us all elements that are less than or equals to b. However, that doesn't tell us the products of a and b that are greater than mid, and the way to find that out is to subtract every element, is to subtract the length of nums2 from the results of this, and that should give us the count. And we just update the value of count and return it. And if I run this code, you will see that it passed. And if I submit it, this is the first time I'll be submitting. Awesome. And we see that it passed and it beats about 55.9%. That is quite fine for me. Thank you so much for watching. If you like the video, please like it, subscribe, and turn on your post notification. I will try to post weekly videos on this channel, and it's a channel for everything about engineering. If you made it up until this point, Temi really, really, really loves you and really appreciates it. And have a wonderful day. Stay safe, engineers.